It's my pleasure to introduce Chang, who is an assistant professor at the Astronomy and Astrophysics Department at the University of Chicago. She's a senior member of the Calvi Institute of Cosmology and Physics, Political Physics. She received a Bachelor in Physics at the Taiwan National Taiwan University and a PhD in Physics at Stanford University. She went to a postdoctoral fellowship at ETH, and she got the KICE fellowship at the University of Chicago, and she is now assistant professor at the University of Chicago. She received the DOA Early Career Award in 2021, and she earned a Salary Fellow in 2024 for early LSST science.
Introduction. Microphone's on? Yep. Cool. Right. Thanks for the introduction, and thanks for the organizer for inviting me here. I want to okay this recording message. Okay. And I'm very glad to be here to talk to you a little bit about what I'm doing and what's sort of interesting in the field of cosmology, and how kind of AI sort of comes into this whole story. So the way I planned it out, the two lectures, the first one is sort of a more overview and introduction of some of the classical AI solutions and problems that we have in cosmology. Some of them might relate to what you're doing. I know there's maybe not a lot of cosmologists in this audience. And the second lecture, I think I'll sort of introduce some more state-of-the-art, more advanced AI kind of techniques that's happening in the field, and a bit outlook to where we're going after that. Okay, so I want to do a little bit of introduction about myself. So as William talked about, I'm an observational cosmologist. I work in large galaxy surveys. I'll talk about what that is. I use this technique called gravitational lensing that I will also talk about what it is later. But in general, the things that a cosmologist is interested in is basically what the universe is made of and how we can come up with a model to explain what we see today on the sky. Okay, so that's what we do. And I want to put a disclaimer here that I cannot claim to be an AI expert in any sense. I encounter AI/ML on a daily basis because this is what we do in the work to solve some of the problems. So in a sense, this lecture will more come from the science side of the AI+Science. Hopefully that's okay, because you probably heard a lot of AI already in the past couple of days. And I thought it might be good in the summer school to just kind of come back to the roots of the science and sort of think a little bit about philosophically how we apply AI to data. Okay, good. And I will also like this general lecture to be a little bit more interactive because we're post-lunch. Everybody is a little sleepy. So let's have an interactive section. First, who from here is from Astro? I expect a small number. Very good. Physics? Okay, very good. Geo? Some? Okay. Bio? Okay, most of you are for bio. CS? Okay, so CS and bio is our general population. Very good. Okay, so now talk to your neighbors and tell them what you do. Say your name, where you're from, what you do.
Yeah, I think Chavez is very big. Let's talk to people. You know, it's not famous size.
Okay, I'm glad you guys are into talking. Yeah, throughout the lecture, we'll have more of these discussion opportunities. So it's good that you're in the right seats. You can talk to people. Yeah, so let's keep that going. Right, so now that I know everybody is into talking, I'm not too worried about this because otherwise the whole lecture is going to be pretty dry, pretty short. So I'm not worried about that. And that aside, I have like discussion slides, but also if you just have questions. I know this is not everybody's field, so just ask, raise your hand and ask me. I think I screwed on my microphone. Okay, let's get started. Okay, so this is a general plan for the day. I talked about this a little already, so there's 2 lectures. The first one, I'll give you an introduction to cosmology, just for people to sort of understand the big questions. I am not expecting people after these 2 hours to go out and be an expert in cosmology, so that's not the expectation. I just like you to appreciate a little bit maybe what we're interested in and what we're trying to solve, and kind of identify the problems that are sort of similar to what you are solving as well. I'll dive into a little bit of a case study for weak lensing, because that's what I do, and point out kind of some of the steps we use AI/ML techniques in there. And then I'll have sort of an overview of just kind of the evolution of AI/ML in cosmology. The second lecture will talk about some of the more state-of-the-art AI/ML applications, and then I'll have sort of a kind of a wrap-up philosophical discussion of what we do to combine AI and science. Okay, good. All right, cosmology. Cosmology is about studying the story of the universe. So we want to have a model that explains from the Big Bang how the universe evolved into what we see today, the stars and the galaxies we see in the sky. Observational cosmology is trying to link this to something we can observe, right? So theoretical cosmology, you can write down models that is kind of first principle right, but observational cosmology, you want to observe the consequence of these different things. And that is sort of what most of physics do anyway. In the past 20 years, this field has progressed significantly because of the abundance of data. I'll talk about that a little bit, but that's kind of just a general statement. And with those 20 years of work, this is sort of what we believe our universe looks like. Okay, bear with me. So who have seen this picture before? Okay, so most of you have. Does anybody want to tell me what it is? You all seen it? Any volunteers? Yes, in the
Arrow
back.
of time.
Sorry?
The arrow of time.
The arrow of time, exactly. Another one, raise your hand over there, yeah?
It's like the Big Bang evolution of the universe.
Exactly. Okay, so this is the beginning of time. There was a Big Bang. The universe expands drastically. This phase is called inflation. At the end of inflation, this is the cosmic microwave background, which emit the first photons we can ever see. It traveled, or like the universe continued to evolve and continue to cool down and expand. Stars formed, galaxies merged, and then the universe generally became more and more inhomogeneous and clumpy compared to the beginning. Okay, so this is out of all the observational data pieced together, this is what we believe happened. And this model is called lambda CDM. I'll talk about that a bit. Right, so out of this model, as an observational cosmologist, we want to ask, what can we observe? So the 2 primary things I'm going to talk about is the cosmic microwave background, so the stuff that emitted right after the Big Bang, and the large-scale structure, which is just this general kind of volume of stuff that became more and more clumpy over time because of how gravity works. We'll talk about that a little later. Okay, so mathematically, you can write down that picture into a very simple equation. Okay, so this is the part that you think, we are AI/ML experts, we work with millions of parameters, this is 6 parameters, it seems like you don't need this. Okay, so this has 6 parameters. It is a model that dictates how the universe evolves. On the left-hand side is how kind of the geometry of the universe, how the universe expands, the expansion rate of the universe, that's this Hubble parameter. And how the universe expands is dictated by what is in the universe. That's basically all this is saying. There's radiation, there's matter, there's curvature, and there's dark energy. Okay, so these different terms kind of occupy different amount of this flow chart. 70% is this. That 5 plus 25 gives this. So not too much are the other two components today. Okay, one noticeable thing is that within the matter compartment, that is about 30%, most of it is dark, meaning we can't see it, it doesn't emit electron radiation. Oh, okay, I think this is not working. Is that right? Hello? Okay, it's working again. Okay, so right, so there's dark matter that we can't see. I'll talk about the reason I want to point it out here is I'll talk about that later, and it's one of the kind of leading mysteries of our model. And then there's this component called dark energy, which has they both have dark in there, but they're not related. It just means that the universe is expanding faster and faster, and we don't know what it is. Mathematically, you can write it down as an energy term, so that's why it's there. And okay, so that is the model. Over the years, it got him confirmed many times over. So it's sort of accepted as the standard model for cosmology, kind of in analogous to kind of the particle physics standard model case. But it's a lot simpler here. Okay, so people have went down and measured these numbers. This is the numbers over there, kind of conformed or like transformed into slightly different forms. But the point being, they're all kind of sort of constrained down to percent level, very well measured, and so on. Okay, so this is where we stand in the field of cosmology. We have this model, okay, it works very well. We measure things to percent level, great. However, the biggest problem of this all is that these two components I just talked about, dark energy and dark matter, don't make a lot of sense, okay? So dark energy in particular has a, if you predict it from first principle, it's 120 orders of magnitude off. That seems pretty bad. Now, what do we do here? Okay, sorry, thank you. Okay, so that's dark energy, dark matter. We know it exists. We know it exerts gravitational force to things around it, but we never detected it. Okay, so that seems like a very big problem, right? You can't identify this particle is dark matter. That seems that seems wrong. Okay, I think people can hear me, so I'm just going to keep talking, and we can go from there. Okay, so we have a model. It has some very major, glaring theoretical problems, but it works. We don't know what dark matter is. We haven't even proved that it's cold. But okay, if you just say, okay, fine, it's a model that works, let's just overlook the theoretical problems and move on. Even if we do that, there's still some problems because there's small inconsistencies that we're starting to observe between different data sets so that the model actually is not generic enough to explain everything observed. And I'll explain that in a bit. Okay, so these are the so-called tensions you might have heard of in different literature, which is just saying that even if you accept lambda CDM, the different parameters are measured slightly differently compared to in different data sets. So the three kind of outstanding ones is this H naught tension. So the expansion rate of the universe is measured differently in late time universe and early time universe. The amount of clumpiness in the universe is measured differently in late and early universe. And then there's this recent kind of measurement that raised a lot of eyebrows and people don't really know what to do about it, is that it sort of says the universe has a kind of negative or like a evolving dark energy. So in the previous equation, when we talked about dark energy, it's either constant or evolving. And this measurement sort of is saying it's evolving, which we never really expect that to be true, but it seems like people are measuring. Okay, just to sort of make this problem a little more concrete, this is the plot for this Hubble tension I talked about. So on the y-axis, it's how fast the universe is expanding today. Okay, you can do it two ways. One way is you measure locally from supernova. I can explain how you do that, but that's a local measurement. You can also measure it from 13 billion years ago from the CMB and extrapolate it to today using the lambda CDM model. So it's a indirect inference, but it's sort of saying if lambda CDM is correct, you should get the same number. Just the fact that they're so close is already remarkable, right? The fact that you're extrapolating 13 billion years of space and time to get the same number down to this level is already pretty remarkable. However, they are different. So this is one of the kind of curiosities or tensions in the field that people think maybe we need a different model, right? Maybe this is caused by lambda CDM being incomplete. Okay, so good. So we're here now. What do we do? Okay, so there's two routes you can do. You can go. One is basically make this work, right? Make lambda CDM work. How does that work? It works by you actually detecting dark matter, or you ruled out enough parameter space that you know exactly what it is. You come up with some theoretical model to explain away that 120 orders of magnitude so that we can accept dark energy is a thing. And then you live with lambda CDM happily ever after, and you move on. Okay, so that is one route. The other route is believe that lambda CDM is incomplete and there's an alternative model needed to explain everything that we've seen. So that requires finding some problems with lambda CDM and then finding some alternative model that can replace it. So that's another route, and then you live happily ever after with this new theory. Okay, so I want to pause here. Talk to your neighbor. Do you have a similar paradigm in your field where basically you're trying to prove or disprove a experiment, like a theory using data? Explain to your neighbor what it is and what are people trying to do with it. All right, 1, 2, 3, go.
Come up with a model that looks kind of sure if it's really your
That was not a lot of time to explain a complicated problem, so I apologize. Does anybody want to share with us what you guys talked about? Do you think your neighbor's problem is very interesting? You'd like to tell us about it? Are you saying your neighbor's problem is not very interesting? Come on, somebody should yeah, speak. Yeah.
Hi. This is like a really hi bio folks. This is a really old one, but like a long time ago, we used to think that we could understand as much as we needed to about heritability just by looking at the number of copies of a gene and the actual code of the gene, for example. But then we had all of these weird instances where we eventually were led to discovering epigenetics because there were like compacting factors in the DNA that were impacting heritability. But I think we only figured that out because our predictions were turning out to be wrong. And epigenetics was the confounding variable that we discovered afterwards.
Interesting. Yeah, that's a good example. Any other interesting examples you want to talk about? All right. Good. Okay, so let's move on now that we know everybody has their own problem solved. Okay, so good. So then you ask, why am I here? I just told you about there's these cosmology problems. Great, but this is AI+Science kind of summer school. So it turns out we have a lot of data, and there's more coming on the horizon. And that makes cosmology sort of a data science problem that we're trying to extract information from a lot of data. The particular kind of data I'm going to talk about today is data from these things called galaxy surveys. So they're surveys in the sense that if you think about traditional telescopes, you think about Hubble, you think about JWST, you think about these things that take beautiful images from space, very colorful, all sorts of things. That's not what we look at. We look at much uglier galaxies where you just scan the sky over and over again. You don't really care if there's an interesting galaxy or not. You just map the sky and map everything that's out there. So in the way we're surveying, or we're taking a consensus or census of the sky. And from that data, you basically get a unbiased sample of the sky where you can do statistics and get at this question of what is the universe doing. So galaxy surveys is one of the things that we do a lot. I'm going to introduce two of them that I work on. One is this thing called the dark energy survey. From the name, you know we're into dark energy. It is a 570 megapixel CCD camera. So it's like this mosaic camera that is made out of like small chips. Your phone probably has a few megapixel usually. So this is like at the time the world's largest CCD camera. It was built at Fermilab. It was Chicago had a big involvement. This telescope, or this camera is mounted in a telescope in Chile, which looks like this. On that telescope, and it over the 5 or 6 years it was operating, it scanned 1/8 of the sky in a couple filter bands. So it's just taking this data, very general capture of the sky. Okay, so this is sort of the sense of data science we're talking about. There's 900 million objects. There's 150 million objects that we use for weak lensing. I'll talk about later. There's that many supernova, that many trans-Neptunian objects. So this is sort of on the sky. At each patch of the sky, we exposure 10, like we take 10 exposures, and it maps out this thing. The reason I want to put this here is you'll see this shape show up later again. This is just turns out to be the footprint we have on the sky for reasons I don't need to go into. Okay, so I want to just show this plot to give sort of a sense of data. So what is this? This is the 635 supernova that we've gotten. Each of these is a light curve of a supernova where over time it exploded, so it got brighter, and then it finished exploding, so then it got fainter. And this each of this is one, and they're just different redshift ranges that you can see on that slide. Okay, so the reason that we have all these curves fitted to it obviously is because people found them, fitted a model to it, and then put it on this graph. So that's a lot of analysis that I'm glossing over, but that's sort of the type of data we're talking about. Okay, so DES is done in the sense that we've done taking data, we're still analyzing it. The next thing coming on the horizon is called LSST. So this is the Legacy Survey of Space and Time. A similar deal, it's a big camera, now even bigger, launched on a telescope in Chile, also in Chile. There was a kind of major milestone about a few months ago where this camera made its way from SLAC in California to Chile without breaking anything. So that's good stuff. And it will start observing basically next year, and we'll start getting data. So the amount of data this is going to get is another order of magnitude. And the main, I would say, groundbreaking thing about this instrument is it's going to take an image of the whole sky can see every 3 days over 10 years. So you'll have a movie of the sky as things like flip up and then die down. And that's going to be pretty transformational. Okay, so just to put some data here. So 20 terabytes of data every day. Over the end of 10 years, it's couple tens of petabytes, and then it will get like this many sort of objects that we predict. Okay, ultimately, sort of the goal is you take these things, put it into your pipeline, and you would want to constrain these cosmological parameters we showed at the very beginning. So the way you read this plot is now we have a 1 sigma and 2 sigma contour on, say, omega m at that level once you combine everything. Okay, so that's sort of closing the loop. That's sort of what we want to get to. I just want to point out this is a former Schmidt AI fellow. Okay, so I talked about DES, talked about LSST. So DES is there. Rubin LSST is here. I just want to zoom out and give people a sense that there's a lot of data also just coming on the horizon from different other experiments. So these are different levels of either in the space or on the ground, spectral or imaging. There's just a lot of data happening. Obviously, once that happens, machine learning, data science becomes important to do a lot of the processing and analysis. Okay. Good. Our second discussion break. Okay, so when I showed the thing saying like I have that many objects, that many petabytes, I'm sure somebody was like, that's not a lot of data. So I like you to talk to your neighbors. What is big data to you in your field? What are we talking about? And then so we start from the science and we say, okay, we have that much data, ergo we want data science or AI to be the relevant tool. What is AI and ML? What is the thing that makes AI and ML the thing for you in your problem that you need to solve? Okay, yeah, talk to your neighbor.
We have a lot of data sometimes. That's the way it's like as far as like a robot.
That's just hang on to that. That's usually- It's not gonna turn- I think the battery. All right, let's stop. Does anybody want to share with us what you talked about? Come on, yes.
I think I'm a healthcare research scientist, so big data in my field. I can access the data in Mayo clinics for 90,000 cancer patients who receive radiation oncology treatments. This is not a big data in most of the field, but for real world healthcare setting, I'll say this is considered as very big data. So AI or ML is an attractive tool right now because I'm focusing more on the patient-centered healthcare settings. So I think it's very attractive because patients are often overlooked because of the resources and because of the urgency of the illness itself. So it can make it more efficacious. It can improve the efficacy, make it more effective, and also perform much better than human because human cannot work 24/7.
Thanks for sharing. I just realized something, which is the people on the call can't actually hear you. So maybe I'll pass this around when people talk. But for people online, what was just shared is a case for healthcare and how for the real world, it doesn't sound like a lot of data, but for you guys, that's like a breakthrough in using these tools for this particular case. Do we have batteries or?
A rechargeable battery, so
Okay.
I can put it.
Oh, it's there. Yeah. Nobody has really complained, so.
No, they
maybe
can,
it's-
as long as they can hear you. Right in the back of the room. Sorry about that.
So I'll just show.
Maybe the second part that.
Sounds good. All right, anybody else who would like to share what you guys talked about? What is big data for you? Sorry for the audio. Okay, well, as long as you guys were discussing, I'm fine with that. But also, it will be nice for more people to hear what you guys were talking about. Okay, but since I am running slow anyway, so I will move on. So I'm going to go through the case study for my particular field.
Oh, yeah, we have
They can't hear us.
someone on Zoom.
Hello? Can they hear or
Oh,
they want to share something?
yeah, so someone on Zoom said that they, let's see, I think the name is Madi, said big data in one of the fields I work on is sensor data in dairy farms and also structured data relating to calving and insemination records. And AI is attractive here since we can predict important factors like insemination results.
Thanks for sharing, Mary. Cool. Okay, so I'm gonna move on and talk wheat cleansing. So if you guys remember the earlier slide, we talked about how structure evolved starting from something pretty homogeneous to something pretty structured. So if you sort of just conceptually slice through this history of time, you can see like matter becomes more and more clumped as we move from early time to late time. Okay, so this is, if you think about it, just like dark matter distribution becomes more clumpy. Okay, so this is the thing that is the thing that we use for cosmology. The slight small issue here is we don't actually see dark matter. Sorry, this. Okay, hopefully you can see it. We don't see dark matter, as I talked about earlier, they don't emit light. So the thing I like to introduce here is this technique called gravitational lensing. Essentially what it's doing is when you have some mass in space-time, it perturbs the space-time around it, causing kind of the geometry to be slightly distorted. And that means that when a light ray travels from point A, it will then get deflected on the way to the observer over here. The deflection angle scales directly with how much mass there is, as well as the geometric kind of configuration of the source, the lens, and the observer. Okay, so what am I trying to say? I'm trying to say, like, even if this thing is not emitting light, there's a way we can see it. We can see it by seeing the effect of this background thing. More concretely, the thing we're actually seeing is how images are distorted. So a circular object, you can think about it as many, many different point light rays. And because each of them bend a little bit differently, the net result is that the circular image will become elliptical. Okay, so the actual observable thing is we're looking for distortion of galaxy shapes, and that tells us where dark matter is. It's not an obvious connection, but that is the thing that is used in this gravitational lensing field. Okay, perhaps more intuitively you can see here where you have, say, the sources before lensing and the sources after lensing. The effect we're trying to see is this kind of small coherent distortion structure on the right that you all can see by eye. And we need to measure that in order to infer where dark matter is. It's very similar to a swimming pool where you see kind of ripples on the water distorting stuff behind it. So it's very intuitive when you think about it that way. We're just doing the whole thing sort of in the sky.
Can I ask
Yes.
a question?
Yeah.
So,
Go.
if I look at a pool,
Yeah.
I know it's distorted because I know what the undistorted pool looks
Yeah.
like. But what about for cosmology?
Yeah, that's a very good question. Okay, so the underlying assumptions we have is that without lensing, galaxy shapes are randomly oriented. And I think you can make that assumption because we believe we don't live in a special place. So we're just looking at galaxies that are just randomly doing its own thing. So if you accept that as true, then any amount of preferred direction is caused by stuff between us and them. Yeah, so that is an important assumption that is not always true, but zeroth order, that's what we're assuming. Okay. Yeah, and people should feel free to ask questions if you have any. Okay, so we measured all these shapes, right? The traditional way people go about and infer cosmology is the following. They take all these measurements of shapes, they calculate some statistics. This particular statistics is saying I take the shapes, I take a dot product of the shapes, and then I go through pairs that are separated by some angle. And then I change the angle, I do it again, I change the angle, I do it again. And that thing turns out to be predictable. Like I can write down the equation that tells us what that curve looks like. And that equation contains these cosmological parameters I talked about earlier. Okay, that's great. So you can write down a cosmological model that has these parameters, predict what that curve looks like, measure it, compare it, and then infer the parameters. Okay, so that's exactly what this graphic is trying to show, right? So if you change omega m, this curve will do this thing. Your measurement is the black points. So you're just like a very simple, there's no machine learning needed here. A very simple fit. We're just asking what that omega m is. Okay, so this is a traditional way people do cosmology. And then you can then take that, do a likelihood analysis, and come up with contours and publish a paper, and everybody's happy. Okay, good. So that is sort of kind of the usual way people do things. I'm going to go through kind of a pipeline from the pixels that you get the image from the telescope all the way to cosmology. These are the steps that roughly happen. I'm going to go through what are the things that people have used AI/ML techniques to apply to, and some of the things that people wish to or are doing more advanced kind of work on. Okay, so this is just a laundry list. You make the observations, and that part is sometimes tricky because weather changes. So at any particular moment where you point your telescope is itself a thing that is not super easy to decide. You can use a network to sort of decide based on weather, based on history, to look at a certain place, to achieve a certain goal. Okay, so that part is that. The second one, you need to take the image, do some image reduction, subtract the background, remove the bias, that sort of thing. You need to calibrate it, meaning I receive that many counts on the CCD. What does that mean for the brightness of the thing in the sky? So think about it, that's not like super trivial, right? So the detector does all sorts of things. So to know that when I measure something, it corresponds to X amount of flux in the sky is something you need to calibrate. So that's the step that you co-addition the images, you extract the objects. So again, think about this. It's not like super obvious. If you just give me a 2D pixel of grids of values, you want to know that is a galaxy, that is a star. It's not trivial given the noise level we're at. So that is another step. You do object classification and artifact removals. So there's all sorts of junk in your data. You want to remove it. You want to classify the star as a galaxy. That's, again, a pretty classical AML problem. You measure the shapes because we care about weak lensing. You need to know the distance. I'm going to talk about this a lot. This turns out to also be a very heavily AML problem. Define a sample, measure the data vector I talked about, uncertainties, do the inference, and then interpret what you get. Okay, so this is how you do cosmology from pixels. These are the things I sort of briefly mentioned. People do apply AML techniques in different kind of levels. I will talk about this in this lecture, and the next lecture, I'll talk about these. Okay, so just very briefly, this is a very classic machine learning problem, right? So this, what you're seeing is a focal plane. So our camera gets an image at one shot that looks like this. And sometimes you get these things that are just coming from stray lights of a super bright star hitting off some strut of the camera that kind of scatters out like this. You get similar things, reflections of bright stars off the aperture, stuff like that. Okay, so this paper, for example, used these images to train masking out these different types of artifacts. This is a pretty straightforward thing you can do. You do need a training set. You do need some grad student to actually mask it and tell them this is that. But after that, you can train it and you can get this. Why is this important? There are obvious things like you want to do cosmology on the clean sample, but there are other things. This example, again, is from the same author. It was a Chicago student. He's actually interested in these super low brightness galaxies. So these are galaxies, okay? You might think like it's a fuzz. What is that? It is a galaxy with very low star counts and very high dark matter density. They're interesting scientifically, but they're very often confused with some artifacts that look very similar. So he trained one of these neural nets to basically classify whether it's junk or not a junk. And you can see the applications basically as such. A similar application, but sort of away from optical astronomy, is this classic example of radio frequency interference. So in radio data, you get certain frequencies that just has cell phones or TV stations or airplanes or whatever that you'll need to mask. The morphology of these things are somewhat complicated and somewhat stochastic. So this is a paper a while ago, actually training a UNet to mask these things with simulated data. Okay, so these are very kind of classic machine learning problems that people do. Nothing wrong with it. It's all good. The second sort of application, people really like to use machine learning is to determine redshifts. Okay, so bear with me. You'll need to learn a little bit of astronomy with me here. So what is the problem? The problem is when you take these 2D images, it's 2D images, right? You never know how far these things are. You just get a 2D image. So how do we know how far they are? We do need that information to do cosmology. So the way you do it is by taking it 5 times in different filters. So it turns out that galaxies have these spectra, and then as they become more and more distant, the spectra moves. And it moves in a way that is predictable and is proportional to this thing called redshift. So here is a sort of an anime showing that. So the way to look at this is, okay, so I have a spectra of a galaxy. As redshift goes higher, redshift is basically how far it is. Let's start from 0 again. Okay, as redshift goes higher, this thing goes to the right. It gets redshifted, so it goes redder, higher wavelength. Okay, as it does that, when we observe in these filter bands that I have here, V, V, I, Z, you get the flux levels on the top. You see that? So they change, Okay, so really we're talking about a 4 number to 1 number mapping, right? So we get 4 fluxes, we want to know redshift. Again, that sounds like a machine learning problem to me, and that people have thought about that 20 years ago and they're still doing this. Okay, so the saving grace in this whole problem is that galaxies fundamentally don't have very complicated spectra. So they have a few types, but not like, they can't be anything. They are governed by physics, and that's why they have those shapes. So people either take that fact and use templates to fit these measured photometry, or use kind of just a machine learning method to map those 4 numbers to a 1 number given some training set. Both of these are subject to the same problem, which is you need a training set, and there are problems with training sets like every other field. Okay, so a classical result coming from these things is like you plot the true redshift versus the inferred redshift, and you plot a 1-to-1 curve, and you see how scattered or whether these outlier structures exist. So this is whatever, 13 different types of redshift codes run on the same data, and you get 13 different answers, and then you try to sort of quantify the bias or outliers of these plots. In reality, what we really care about is actually for a sample of galaxies, what is the redshift distribution? So in the end, you get like a N of Z, kind of a redshift distribution of a bunch of galaxies. And again, here are 1, 2, 3. There are 7 different codes, give you 7 different answers, and then you can discuss what is good, what is bad. You can see that the smoothness and the coarseness of these different curves look different, and that's just coming from different priors and assumptions in the different codes. Okay, so as time moves on, people started using more and more fancy machine learning methods, and the past like 5 years ago, we learned that there's this thing called self-organizing map, and people start using it. It's really just a different technique to do mapping of color space to kind of a 2D space. So you input however many 5 or 6 color values, and you try to organize it on a kind of arbitrary 2D parameter space. So that's what SOMs are. It just allows you to better visualize and classify things. Okay, that's fine. So people do that. It really doesn't really solve the spectroscopy problem, doesn't solve the training set problem, but it bypasses this assumption of assuming certain templates or certain things. So this method, again, it's a new machine learning method, but it's not bypassing the fundamental physics problem. Okay, so the physics problem. So I want to put this plug here to just remind people, right? Machine learning solves a lot of things, but sometimes it doesn't solve the important physics problems. Here, I'm using spectra as an example that when you selected that spectra sample to train on, usually each paper will have a paragraph saying where the spectra came from, and it usually came from a bunch of things that are not related to each other, and they could have their individual selection effects. And this paper basically shows that, yes, there are these selection effects that if you don't account for, it's going to cause biases and so on. So this is just kind of a reminder that machine learning helps some things, but it doesn't kind of give you a free pass in solving some of these harder problems. Okay, right, so that is my point. Machine learning oftentimes helps speed up things, and sometimes does help solve physics problems, but not always. So if you can turn to your neighbor and discuss a little, if you have a similar problem that you're trying to solve, where machine learning speeds things up or gets you some benefits, but doesn't really get to some other problems that is kind of the more fundamental issues in your field. All right, so have a chat with your neighbor.
I don't actually. Like pretty similar. And so it's make a picture. Still not learning.
All right. Does anybody want to share with us what you're talking about? I want to learn about everybody's problems. Come on, you guys are talking.
So, we were kind of talking about the problem of, climate change and forecasting. And it's a very complex physical problem, and you can build models to predict things into the future very well. That outperforms your traditional techniques. But in terms of like model interpretability, it's like pretty hard because it's so complex. So the model is predicting whatever you want to predict, but you're not really understanding like the underlying physics.
Great, yeah, that's a great example, and I think we'll touch upon that a little bit in the second lecture. So for people online, the example was for climate models. Because it's so complex, you can possibly predict things, but you may not know why the machine is predicting what it's predicting. And that sometimes is the thing we try to understand. Any other examples?
So I think it's similar, but like in neurobiology, some of the models are getting good enough that you can tell if one neuron, like which neurons a single neuron is talking to or sending information to. But it doesn't really tell you if that's, what the brain should be doing,
Right.
or if it's controlling behavior, if you want to alter behavior, if you want the neuron to be sending to those neurons or some different neurons, or how to change it.
Mm.
So it's descriptive, but it's not predictive, and it doesn't give you understanding. It just gives you sort of a description of the state.
Right, so the example given is for neurons, sorry, you can map out what it's trying to do and even predict it, but you may not know why it's doing it, or like what, what is the mechanism in which it's doing that. So yeah, okay, so what I'm hearing is interpretability is a big problem, that people are not super satisfied with the state of the art. Any other different kind of angles? Yeah.
So I do my work at the intersection of medical robotics and AI. And in my situation, I'd say it's more of a human psychology issue, right?
Mm.
So I don't think that human beings are at least ready right now to give up their bodies to have AIs operate, right?
Yeah.
So
think
it's
that's
not
true.
necessarily an issue of how efficacious the AI models are. It's
Yeah.
more an issue of human psychology and human trepidation, right? I'm not gonna just sit there and have a machine work on me.
Okay, yeah, that's another good example. So this is, the example given is, medical robotics. So, it sounds like, so, yeah, I'm telling the people in Zoom, so it sounds like the issue here is that cannot be solved by just a faster machine, is to like convince people that, you should give up your own brain and that this other thing, operate, your behavior. That seems like, yeah, another not just by throwing in more computers, you can solve that problem. Any other, I thought there was, yeah.
Yeah, I mean, it's like in the field of work, what we really care is like to understand what features really affect like the height or traits, and not really about predicting things. So you want to know which part of the genome affect another part. And I feel like good old-fashioned statistics solve this problem really well. And I've never seen any machine learning methods that really kind of like outperform such a thing.
Okay, that's an interesting example. So this is human genetics, trying to have a certain genome predict a trait. What the audience was saying is, what William was saying is, like traditional methods work pretty well, and doesn't seem like there are new machine learning things that can replace that. Okay, so that's a good collection of examples, and I think that's something I want you to sort of keep in mind as we go, right? What are the important questions that we're trying to solve, and how do we get to using these powerful tools to actually solve these problems? Okay, so in the last like 2 minutes, I'm just going to sort of step back, and I want to give you a kind of a historical review of how I see cosmology evolve as AI kind of picked up. And maybe just inspire you to also think a little bit in your field how AI came into the field and how it's going forward. So as I see it, there's roughly 3 phases how kind of AI came into cosmology. So like 1990 to 2010, so this is like old, right? So a lot of people probably were still, I don't know, in kindergarten. So that's kind of the first time people realized that data can be more than a GIG student can handle. Machine learning starts to kind of become relevant. So this is a paper, like you can see here, 1991, where people were already using kind of neural nets to separate stars and galaxies. Okay, so it goes way back. It's not like a new thing. And I think that's true for every other field that people are working on here as well. So by that point, like the methods people are using are these very classical things: random forests, PCAs, Gaussian processes. Some people may not even call them machine learning today, right? It's probably just statistics for you. So that's kind of phase 1. Phase 2, 2010, 2020. This is sort of when GPUs, again, like I'm some other historian might correct me for this, but this is how I feel. That's how like GPUs became used in science. And then we started to sort of just have free range on like, this is so exciting, we should do everything with machine learning. And then a lot of people started using CNN to do things, deep learning, transfer learning, reinforcement learning. This paper I sort of already cited earlier, but this is, I remember vividly because Joel is like a software engineer in our group, and he was like telling us this exciting new trend of CNNs and like explaining to me what deep learning is different from normal learning. So that I remember, and that's sort of where most of the field started picking up. And then there's today. So today, how I see it is AI is everywhere, and generally people go in 2 directions. One is just sort of giving up trying to understand like what the thing is doing, but just throw a lot of data at it, like a lot. So that's like yeah, like this paper is sort of in that range, but I think it's also trying to explain some of it. But that's one direction. And the other direction is kind of stepping back and trying to think in a more classical way how we do science and interpreting these AI machine in that context. So I'll give some examples of the second thing. And how I feel like now people are sort of, okay, now we know this thing can be very powerful, let's try to use it in a more principled way to do science. Okay, so that's how I think our field is going. And we're at time, so I'll let people go to coffee break. But during coffee break, you can discuss the following. Think about how introduction of AI ML techniques in your field has gone. Does it have a similar trajectory? Some of you might be too young to know what happened in 1990. So ask your more senior colleagues what happened then. And talk a little bit maybe about like what is next after these trends. I think Simona wants to say something or no? No. Okay, cool. All right. So go off to take your coffee and then talk to your friends.